Thanks for coming to the second seminar at MIT Robotics. It's a pleasure to introduce Michael, actually the first person to visit us at MIT Robotics seminar after a year and a half. So thank you very much for making the trip. It's fantastic to have you here. Michael Posa, he's an assistant professor in mechanical engineering and applied mechanics at the University of Pennsylvania, where he directs the Dynamic Autonomy and Intelligent Robotics Group at the well-known GRASP Lab. And Michael, for those of you that don't know him, he's an authority or a gourmet or a connoisseur of contact. His group develops techniques, either model-based or data-driven, for robots to explicitly reason about and plan through and control contact. And I'm sure that he has much more to say about his current work. But Michael has also a record of influential contributions in explicit thinking and algorithmic reasoning through contact. Before going to UPenn, he graduated from in 2017, working at the Locomotion Group. And he gave us one of the, I would say, most influential contributions in manipulation in recent years. A direct method for trajectory optimization of rigid bodies through contact, or as many of us know it as the Posa paper. It's a work that showed that, yes, that it is possible to embed explicitly in a trajectory optimization framework the same kind of constraints that we use to simulate contact. And it's a work that, among many other things, it made robotic flamingos walk. But also then just in a few years, it has turned into a classic and has motivated many researchers down that path. Michael has received Best Paper Award at Hybrid Systems and Faculty Research Awards from Google and Toyota Research Institute. So Michael, thank you for making this trip back home. It's great to have you here. So please, the stage is yours.
Great. Thank you so much for that the very kind introduction, Alberto. It's so exciting to be anywhere in person, but much less MIT. You know, the first robotics seminar that's back in person. That's an honor, or external speaker at least. You know, I don't know what to do. I'm not sitting at my kitchen table anymore, so it's weird. Okay, so I want to talk about a lot of the work that we've been doing lately, right? This is all basically in the last 2 or 3 years from my lab. And I'll show some videos that I'm sure everyone has seen before, right? So robotics have made great strides, right? You can look at the Boston Dynamics as a shining example. I mean, this is super cool, right? It's running, it's doing parkour. It's not human parkour though, right? There's still a big gap. Okay, this is not that we need robots really to be YouTube stars, but there's a huge gap between what the robot is doing for parkour and what the humans are doing. And you can take that as well, and you can send it to things like in-home actions as well. So here we have Iron Chef Morimoto chopping carrots. And what are some of the big distinctions, I would think? There's a lot, right? There's a lot of things we could pick up that the people do better. But one that I'll kind of focus on is that the robot, as great as it is pretty limited to carefully planned interactions. Okay? It knows at the very beginning where it's going to step, in what order. It's going to go off these walls, and it's going to touch this, and so on. And this has all been very carefully scripted, and is very distinct from what humans are working on. So I want to put this sort of as my motivating picture right now for a lot of the work we're doing. Your robot enters a room. Okay, it's a kitchen or it's a workplace, something like that. It's not a room it's seen before. It's filled with objects that maybe it hasn't seen before. And it needs to accomplish some tasks in this room, whether that's cooking something or maybe some assembly task. Okay, so what does it need to do? This is not the only way you could approach this problem. It's about how I like to think about it. It needs some understanding of its environment. Okay. How things move, what they are. Maybe this is coming from vision. Maybe it's coming from some other setup. And then it's going to need to take some actions. You need to pick actions and choose to execute them in the interest of some goal. So what's going to go wrong? A lot, right? Could go wrong. There's a reason robots aren't in our home yet. But things that excite me in particular kind of relate to the challenges of going out and touching the world and interacting with it. Okay, so The world's very complicated, obviously, right? That's no surprise. There's internal dynamics, degrees of freedom. There's different surface properties. This thing is made of rubber. This thing is made of glass. They're going to behave differently. Geometry of these in-home objects is very complicated. More to the point of this talk is that when you start touching stuff, the forces that you generate are discontinuous, or at least nearly discontinuous in the actions you take and the state you're in. And they're very difficult to model. Right? This is inevitably the sticking point of your favorite simulator, what it spends the most time thinking about. The biggest differentiator, right, between control strategies and learning strategies and simulators is how they handle this interaction. Right? That's I think where a lot of the key challenges are. Okay, and then inevitably, whatever plan you make as a robot, it's not going to go exactly as planned, and your robot's going to need to react. And particularly, I'll focus on things that cause contact to be broken or stick slip to occur. Okay. All right, so I want to talk, kind of give an overview of our recent work on these themes. I'll start with control, and so we'll start by thinking about if I have big impacts, if I'm jumping, let's say, so my robot's jumping and landing, how do I design control strategies to handle that sharp change? Okay, and then a little more theoretical, how do we do feedback in a few different settings in these multi-contact problems? And then because everything we do in that second bullet point requires a simple model, we'll talk a little bit about how we might generate a simple model from a complicated system. And then the second half of the talk is going to be about learning. Right? And particularly, I'll make this kind of forceful, controversial maybe statement that I think differential physics is not enough, and that if you base your approach on differential physics and deep learning, you might be missing some key parts of the problem, and then our solutions to try to address that. Okay. Before I jump in, I want to make the point, because we're all in person again, right? Ask questions. Raise your hand or just interrupt if you have questions. Make this a conversation as much as possible. No one really wants me to sit up here and talk to myself the whole time. So let's take advantage of this. Okay, so we'll start with jumping. So here's our Cassie in our lab. It's doing some kind of relatively modest jumps. And so how do we approach this problem? The traditional approach looks something like this. Well, we have some kind of hybrid plan. We have a crouch. We launch ourselves on the air. We have some kind of flight phase. We land again. There's these three distinct modes, and we're going to switch between them. Okay, we're going to detect when those mode transitions occur. We have some kind of nominal model of what's going to happen. That model involves some kind of instantaneous hybrid switch. What does this look like in practice? These are our joint trajectories from the actual system. The x-axis here is milliseconds. And we can pretty clearly see that velocity changes very quickly. Right? Accelerations on the order of hundreds of radians per second squared, but not instantaneously. Okay, 10, 20, 30 milliseconds sort of for this event to resolve. And that's caused by internal compliance in the system and just the fact that it's not a true nominal rigid body. Okay. How does this affect control? So here's our beautiful hybrid plan from whatever our hybrid control strategy looks like. We have some pre-impact state, we have a post-impact state, we have a jump. Okay, this is our hybrid strategy. And what we would do with our feedback is say, okay, before the impact, we track the red thing, we have a jump, then we track the blue thing. Right? That looks great. Detecting that impact event is tricky, but even worse is the fact that it's not an event. Right? It doesn't occur instantaneously. It takes some period of time to resolve. And now we have a problem, right? If I want to do any kind of feedback, which is, what am I tracking? Right? I have my velocity is somewhere between the v minus and the v plus. Maybe I can measure it, maybe I can't. But it's definitely not either of those two things. It's somewhere in between. And if I now say, OK, let's take a hybrid plan and a hybrid strategy. I take my gain, I multiply it by my error. And what is my error here? Right? I'm in this middle ground. My error is big. I multiply it by gain, it's big. I do bad things with my controller, to speak colloquially. I mean, my controller is not tracking either of these. And so you're left with the fact that your controller starts injecting disturbances when you land. Okay? And people who have worked on particularly things like Lego locomotion see this all the time. Right? Impact is hard to deal with. Therefore, I need to do something to my controller. I need to drop my gains really low. I need to blend my pre and post-back controllers. I need some kind of hack to make this work out, because no matter which thing I try to track, I have a lot of error. Okay, so we're going to take this idea here, right, and try to understand it a little bit better and say, what should we do that's better than just say set my gains to 0? Okay, can we do something a little bit more intelligent than that? Okay. And what this really comes down to the fact is that during this period, that force, that impact impulse, lambda, is changing very quickly, but we can't really measure it. Okay? It's happening too fast for us to reliably respond to, so we need something that's going to be invariant to it. So this is a very simple idea. This is work done by Will Yang and my group. And the very simple idea says, well, your velocities are changing very quickly in a way that's hard to measure and hard to respond to, so don't track them. Right? That goes back to this idea of low gains. But only some of them are changing. And in fact, only some particular subspace are they changing. And so there's this impact-invariant subspace, which is essentially the set of velocities that are not changing that fast during impact. Okay? And then if you make this projection, it takes your, over a sequence of trials here now, takes your joint velocities from the left, maps them over to the right, and now the right is a nice space where we can do control. Right? Things are not changing too quickly there. We can measure it, we can estimate it, we can do feedback. Okay? So very simple strategy here. Right? Given an impact, generate this linear projection, and do your control in that projected space. You can do this for things like PD control, where it's obvious what to do. You can do this for your favorite QP-based model predictive controller that's tracking outputs. The projection becomes a little bit more complicated, but it really is not in practice that hard. So I like this work. This is a very simple strategy. The outcome from this is that you empirically get things like more robustness to uncertainty in the impact event, more robustness to things like stiffness in the contact in simulation. Here we're sort of demonstrating that if the terrain goes up and down, we have smaller spikes in our effort, which is what you really see. You really see the controller reacting badly in this window, and that leads to better tracking performance. And we can do the same thing in real systems. So this is Cassie here on the left without the projection, on the right with it. They don't look too different until you start to focus on the event itself. Here, the controller actually recovers, but if you focus sort of right on the ankles there as it lands, there's a pretty violent shaking that occurs during the landing. And that is explicitly a switching controller behaving poorly, attempting to switch and getting it wrong. Okay. So that's neat. Tobias, yeah. It's lower dimensional, yeah. Those gains go to 0. Essentially. So your gains in the subspace that are subject to impact are essentially zeroed out. And the gains that are not subject to impact, you can maintain. Right. So it's a generalization of this idea of lower my gains, but lower some of them. Lower the ones that are related to the uncertainty.
So which joints in Cassie were in the null space of the velocity?
It's not necessarily the joints themselves, right? Because obviously it's a projection, but it's things that relate to like roll and yaw of the legs, and you can kind of see that here, right? The ones that are shaking are these, like I said, the hip roll joint shakes a lot, and that's one that we largely cancel out.
What's the rule that you use for the projection to generate the projection?
It's very, very simple. Okay, so if you look at the impact law, it's essentially the subspace of velocities here that are unaffected by applying impulses lambda. So that's a mass matrix Jacobian there. So this is a pretty pessimistic viewpoint of control, right? This is to say, an impact's going to occur, I can't do anything about it. So sort of give up. But at least give up minimally is kind of the way I would think about that. Can we do better in other domains? And so here's sort of our take on feedback, particularly using tactile sensing here. So what if we measure the force right, during impact? Can we do better from a control perspective? It's hard to use tactile sensors, right? A lot of common approaches are things like move to touch or sort of hybrid mode-driven approaches where you achieve some part of your task and then you switch to some other controller mode. It's tricky to do in practice. It's tricky to respond quickly to these things. You end up with some heuristics for thresholds and the like. What instead we're going to do is try something very simple. We're going to say, take the measured forces, so now we're going to use lowercase lambda here, and feed them into our controller. Okay, so our controller directly depends on lambda. It gets some kind of hybrid nature from that dependency, but not explicitly. So just quickly, I'll contrast this, right? You might have, say, pure state feedback. Okay, so state feedback doesn't have to do mode detection, which is good because I would argue mode detection is hard. It doesn't have any tactile feedback, which is bad, right? It's not actually responding to forces in any way, but it's relatively simple. You could say, okay, let's do something purely hybrid, where now I switch depending on what I'm touching. Okay, now I end up with some exponential number of parameters related to my mode switching. I have to do mode detection, which is scary, but I get this sort of the ability to respond to touching the world, which seems important. We're going to live in some kind of middle ground here, where we're going to design a very simple controller Okay, linear in state, linear in measured force. We don't have to do mode detection, right? We don't have to take lambda and threshold that. We just pump it right to our controller. We get some kind of tactile feedback. We don't have the full expressive power of a hybrid policy. Therefore, our controller is simpler but less powerful, right? So this is a middle ground, but one that's shockingly easy to implement. Okay? This work in particular, we focus on this particular structure here called a linear complementarity system. If you've seen this before, this will look familiar. If you haven't, I wouldn't worry too much about it. It's really just encoding the relationship between force and state via this non-convex quadratic condition. We can handle things like soft, but in the sense of non-instantaneous impacts, but relatively stiff, as you'll see, contacts. I'll gloss over the details. We synthesize a controller using Lyapunov functions. We solve this as a BMI, this non-convex optimization problem. And we can scale this to about 10 contacts right now in terms of how big we can solve. So if you do 2 to the 10, that's about 1,000 modes. So this is offline computation. Design a control policy that's provably stable and generate a Lyapunov function to go along with it. Okay. And then we apply this to our Carpool example inspired by work here at MIT, where this is a Carpool we built in the lab. It has these big foam walls that it can slam into. And no surprise if you design a controller, say something like LQR, that doesn't know about the walls, the act of touching the walls is destabilizing or can be destabilizing. On the other hand, if we take the same controller in terms of the state feedbacks, we impose some constraints on our BMI, we can get a tactile feedback policy that responds to impact, and it works shockingly well in practice, right? A little bit of sysid went into this, but really not that much. And certainly our notion of like linear spring for this foam wall is totally wrong, but it seems good enough, right, with the force sensors. The neat thing here that I think is important to stress is that these controllers really only differ in this 20, 50 millisecond window where you're hitting the wall. It's a relatively short period. And you might be tempting to say, well, it doesn't last very long, so what I do doesn't matter that much. And that's empirically wrong, at least so I would claim. Right? It matters a lot what you do in that window. And therefore, responding to that force can really have a big effect. Okay. This is very recent variation on this work. I don't have all the details today because this is something we just sent to ICRA. But we're trying to do this in real time. Right? So that was BMI, solve it offline. We're trying to do it in real time. So we're going to formulate an MPC problem, same class of systems, this hybrid MPC problem, where we have some, our linear complementarity dynamics over some horizon with some non-convex quadratic constraints in them. One thing you could do here is convert this to an MIQP. So this is kind of a standard thing you might try. Of course, if you do that, you're not going to be solving these particularly fast. And I want to stress as well that this horizon n really matters a lot. If I want to design a controller that's going to react and do things like brace against walls or make and break contact intentionally, it needs a prediction horizon where it can see those in the future, right? A very myopic controller is not going to work here because it can't see the next mode that it might change into, which of course scales the size of the integer variables or the optimization problem. Okay. I would argue that this is true, that this is intractable globally. Right? Maybe someone will come prove me wrong, but I would argue it's probably intractable. And so we need something suboptimal, but good enough. But it's also important, I would say, that we need something that's good enough that also does some mode exploration, is not totally limited to sticking within its planned guess as far as what it's going to touch and when. Okay. So what we've done is we've implemented this via ADMM, and I'll leave out the details here. But just in terms of scalability, we have something like a prediction horizon of 10 steps, about 10 states, about 3 contacts. We have a kind of a pivoting example in addition to the Carpool one here. So it's a pretty big integer problem here. And we solve this right now at about 20 hertz. I think that easily could become 50 if we code it up better. So that's sort of the time we're looking at right now. The nice thing about ADMM for this problem is because we use a consensus formulation, for those who know ADMM, the hard part of the problem, which is these non-convex constraints, we actually can separate in time. So we can solve them all in parallel, but more importantly than parallelization is the fact that they all become independent from one another. So we've taken the hard part, which in this formulation here, everything is coupled in time, and we've broken that up to where they can be solved much more quickly. Right? So it turns out for something like this example here, we actually are solving MIQPs, but we're solving very, very small MIQPs, just a lot of them. As long as they're known ahead of time, it doesn't really matter. Yeah. So in the Carpool is time invariant. We have a pivoting example that we relinearize every time. Empirically, it does pretty well. I don't know that I can say more than that. We do measure things like that. So we'll go on in sim and say compute the true MIQP solution versus the thing we're coming back with. And it's important to do that carefully. For these scale problems, it often does well. I don't know. I mean, it requires a little bit of tuning sometimes. We have some like finger gating style problems as well, toy problems. Friction is trickier, it turns out, than making and breaking contact, for what that's worth. But yeah, I can't say anything formal, and I don't think I will be able to. OK. Trying to keep an eye on the time. So these kind of strategies, as happy as I am about the speed, they're still relatively small, right? It's not Cassie, right? We're talking about dimension, right? And so how do we get to this goal of robot goes into a world and takes actions in real time? It has to manage its complexity somehow. And so in the world of legged robots, what does that look like? Well, we take something like our Cassie, which has 20 degrees of freedom and so on, actuators and contact points, and we need to do something simpler. So some kind of low-dimensional representation, some low-dimensional embedding. For instance, inverted pendulums, right? So make my robot act like an inverted pendulum. This thing is way simpler. I can do control over here, right? And this is basically, I would say, how a huge chunk of robotics works. Certainly, if you look at like the Boston Dynamics videos, this is what they're doing, right? Maybe they're not using an inverted pendulum, but doing something like this, right? Take your simple model, do some planning with it, and then track the simple model, maybe with a QP. All right. So where does the simple model come from, right? And I said already that BDI doesn't use pendulums for their parkour. They're doing something else. So basically, they had to come up and create it. Right? They said, for this task, a pendulum works really well. For this other task, it's not expressive enough because a pendulum can't do parkour, so I need some more degrees of freedom and some actuators and the like. And so basically, we've kind of set about trying to answer this question from an optimization perspective. If I want to do real-time control, I need a simple model. Where should my simple model come from? Can I optimize that offline? Okay, can I take some understanding of tasks that I might want my robot to accomplish, walk at certain speeds, up and down hills, and the like, offline, crank through, and come back with a 3D model that I can then do real-time control with. So we formulate this as an optimization problem. You first kind of have to recognize that if you want to make your robot act like a simple model, that's a restriction, right? It can now only do things that inverted pendulums can do. So that's a constraint. Okay? The problem we formulate is to say, find a model that's capable of high performance across your task distribution. So what is the expected value over the distribution of solving a task while acting like the toy model? And then we compute this cost thing here via trajectory optimization. And so we get a bi-level optimization problem here. Okay, so we have trajectory optimization at the bottom level and this model parameterization at the top level, which we solve via SGD. So for things like Cassie, right now our examples are start with the inverted pendulum and try to improve it. Take like a 4D task space, and what we kind of see on this plot on the right here, is that as the model iteration count goes higher, right, the model becomes more capable. Right? Our expected value of cost goes down, and we see something like 30, 40% kind of cost reductions in theory. What we can then do then is take that toy model and embed it into some kind of real-time planner. So we can do, real-time 1 Hz planning for footsteps, and then do, 200 Hz, 500 Hz, kilohertz level QP style tracking controller. Unfortunately, this is all sim right now. I hope to have real-world videos to show this soon, but not quite yet of this in practice. That should be, knock on wood, in the next couple weeks. So, all right, before I switch to learning, any questions or Terry?
What class of models did you search for?
We have trigonometric polynomials. I think we've explored various degrees, but yeah, nothing terribly rich.
Do you think of the bi-level optimization as achieving a task relevance in the model? I mean, if you change the cost function, do you get a very different model out?
Yes, sort of. I mean, you definitely get a different model. I don't know how very different, but you definitely, you're embedding task relevancy to the model. Yeah. There's some things we're not doing that this problem doesn't solve. Maybe I'll throw out there since we're talking about it. is this idea of using trajectory optimization under the hood is very optimistic. It says the model I get back is capable of high performance. It does not say you will achieve high performance once you take that model and you do all the stuff with it, right? Do your real-time planning and control. So there's a gap there where I think it's really nice the way it's been defined because it's a statement about the model itself, right? Kind of agnostic to how you might use it. But if we want really high performance, maybe we need to do something that looks more like on-policy training. So optimize the model with the idea that this is what you're ultimately going to do with it, real-time MPC.
That would be assuming the trajectory optimization.
Yes. Which we put a lot of work into making good enough. But yeah.
So you don't have any guarantee that the simpler model was higher?
In practice, no, we don't.
Besides the
It can, but will it? Yeah. It's
exploiting something about the simpler model. Reduce the cost.
That's the idea. I mean, so you're always, in trajectory optimization at least, we get a lower cost than, say, LAPM. And we get a higher cost than had we not used a simple model at all. Because again, simple models ultimately are restrictions. I don't know if that answers your question. But I can't do trajectory optimization in real time anyway. So that's a theoretical optimal, but that I'm not going to achieve. OK, so the rest of the talk, I'm going to switch gears a little bit and talk about learning, right? So this is everything up here. We have a model to start with. Where does that model come from? Again, my robot's entering a world it hasn't seen before and needs to decide what to do. All right, so here's sort of the motivating problem we'll use for the rest of the talk. All right, you're given a time series of data in IC3, so poses in time, and what's going on. Okay, and the rest, everything else you have to figure out, or you have to infer. We can look at this and we could probably know roughly what's happening here, right? There's some kind of bouncing thing that happens, maybe twice, 3 times maybe, okay? It kind of looks like it skids to a stop at the end, right? Maybe we don't know exactly what happened here, right? Exactly what object generated this motion, but we have some idea of what happened, right, intuitively, right? So this is, I want to put that in your head because this is not an impossible problem we're posing here for learning. Let's make it even simpler, something like this. Okay, you're given what's clearly a bouncing ball. Okay, you're given this data and figure out what happened. Okay, there's a problem with deep learning here is that networks are biased towards simplicity, right? All the regularization, all the structure we typically impose in a deep learning problem. If I say, given my state, predict the next state, there's an inherent bias there to things like low Lipschitz constant or simplicity or smoothness. Okay. What does this function look like? It's not smooth. It's not simple. Right? If I think about the mapping from position and velocity to next velocity, here's our impact right here. Right? This is things that bounce. This is things that didn't bounce. It's a small slice of state space, but it's a very important one. Right? Impact is sort of the interesting thing that's happening here. If I miss this, then I kind of miss the key properties of the system. So this is not simple, right? This thing we're trying to learn. But something is simple here, and that's the ground. Right? The ground is flat. The ground is simple. Dynamics are not simple. Okay, so that's sort of the first insight here. We'll come back to that later. First, I want to just kind of stick with the naive deep learning. So let's do a numerical experiment here. Turns out that data is from a cube. Here's a simulated cube. And we're just going to look at the role of stiffness. So we're going to take a single parameter so we can vary it and do it in simulation. And we're going to try to understand how this affects learning. So there's a few hypotheses. One is everyone I think will agree with is that stiffness creates chaos. So a very stiff differential equation is going to be difficult to predict, period. Okay, and so we'll try to take that effect out a little bit because it's just hard in general. The second is that stiffness is going to hamper our training. So it turns out we have really a lot of trouble training these things. Even grossly over-parameterized noiseless problems are tricky to train. And then lastly, it's going to, because it conflicts with deep learning inductive biases, I'm going to claim that stiffness hampers generalization. So we'll kind of look at this a few different ways. How well does an oracle do on our data with noise? What's the gap between the oracle and the training loss? And then what's our testing loss as compared to training? Okay. And we're going to do this over a few different stiffness parameters. Here's the medium stiffness version. It looks roughly realistic, right? It's not bad, but it's definitely not quite right? It sinks through the ground a bunch. Soft is going to be way softer than this. and stiff will be something that looks like a real system. And then we're going to do some Majoko. And lastly, we're going to make this as easy as possible. So I would encourage anyone who doubts the following statements, because they are totally empirical, to try themselves and see if they can do better. If you can, I will thank you personally. But we could not. All right, so we're training on single-step predictions. We have no distribution shift. We've optimized hyperparameters for each test case as best as we can via a pretty exhaustive search. All right, so the first question is, how hard is this problem, period? Well, yeah, OK, so stiff systems are harder. Okay, in Oracle, the true model in SIM with noisy data does worse. No surprise. Okay. Training error is also problematic. Right? Orders of magnitude difference between training on the stiff system versus SAW system. The training on these is hard. This is really just, can you memorize the data, right, at the end of the day? And it turns out that's tricky, because the optimization landscape is nasty, as we'll see. And then lastly, generalization error. Same story here, which is, I think this is the theory, at least, is this is coming from mismatched biases between the underlying data and the network, and that as the amount of data goes up, for the stiff version, it just doesn't generalize particularly well. And in fact, the generalization error hardly budges over time. If we do this on real data, so again, this is our a deep network fit to data, our best attempt at choosing architectures and the like, trained on predicting single-step, single-frame pose changes given motion capture. And it does OK, right? It gets bulk motion roughly correct. It does very poorly on things like orientation. The simulated cube, the predicted cube goes into the ground. It doesn't come to rest on a surface. It doesn't even come to rest. It just kind of slows down over time. So it does OK. Okay. All right, so we'll try to do better. That's the next step here. So here's what we come back with as a simulator, as a predicted model. It's not perfect. Right? You can look at like this one, for example, and see that the real cube rolls a different number of times. Right? We're not about to take this and go to the craps table and start predicting outcomes of dice tosses. But it does pretty well, and it captures sort of key parts of the system. Right? It doesn't really penetrate all that much. It comes to rest nicely and learns something about faces. Again, this is trained purely on that pose information. Okay? No context sensing, no mode detection, just that SC3 trace in time for a sequence of data. Right? The fact that it's a cube is something we learn, right, as well. Right? We're drawing the cube, but that's the learned cube. So how do we think about this problem? There's a few sort of two insights here that are important. First insight comes from representation. Okay? If I think about how a simulator works, right, your favorite robotic simulator, it does something like this. It goes and it computes the smooth parts of the dynamics, gravity, actuation, et cetera. It also goes and computes some things related to contact, geometry, sign distance functions, friction Jacobians, and the like. And then it takes those two things and hands them off to some kind of solver. Again, this is where all the innovation is in simulation, is what goes in that red box. And it spits out a net force. Okay? And all the hard part of this problem, all the nasty, non-smooth, discontinuous part is in that contact force solver. Okay? So what are we going to do instead? We're going to learn the things that go into that contact force solver. We're going to learn things like contact sign distance functions, contact Jacobians, and smooth forces. Okay? The reason we're going to learn these things is because we expect these things to be nicely behaved. Right? These things are simple, going back to this bouncing ball. These are simple functions we're trying to learn. Right? And we've handed off the difficult part to this red box here. Okay? This is really essentially an implicit representation of the dynamics. Okay? I'm not going to find f of x directly. I'm going to find things that generate f of x. Okay? And again, so I think the reason I love this so much is because we're learning functions that are aligned now with the biases of a deep network. Right? If you say find the smoothest expression of my data, and go learn geometry this way, that makes sense. Right? That's a well-posed problem. Okay. If we want to simulate, we then take the thing we learned and we hand it off to our favorite physics solver. That's not quite enough. Okay, so that sort of addresses representation, but it doesn't address this problem we saw earlier with training loss. So that I think kind of goes to this idea of generalization and bias mismatch, but doesn't affect training loss. So let's think about a high school physics experiment here. We have a block on a table, and we're just trying to figure out the coefficient of friction. Probably all done something like this. We're going to assume we have a single data point of sliding. Okay, right? And so what is the change in velocity as a function of mu? It looks like this piecewise affine function here, where if my mu is very large, then I have sticking, and so v doesn't change. And if mu is small, then I have sliding. And I have a single data point here, which says I generated this particular force, and therefore coefficient of friction is 0.2. Okay, we all could have done this given this data point in high school and figure this out. Let's make a loss function out of this. What's my prediction error? Looks something like this, right? Which is a nice, beautiful quadratic function around the optimal, but flat if I predict sticking. So what this says is if I'm predicting sticking, if I guess mu that's too high, gradient descent is not going to work. Okay, I have zero gradient out in this regime off to the right here. Toy problem, one data point, maybe lots of data gets better. Okay, but gradient descent here is going to start to struggle. What's a slightly more complicated example? Let's think about learning a step function. Okay, a frictional step function. So we have sort of data in the middle here, right? That corresponds to sticking here for friction. And what's our loss function? Loss as a function of the location of the step, right? We have a single parameter here, just a step location. It's being animated here. It gets the global optima correct, right, at 0, but it's very nasty, right? Zero gradient almost everywhere. A big sharp spike right at the origin, because that's all the sticking data stacked up on top of itself, right? Very poorly conditioned loss function. Hard to optimize over something like this. You can imagine this now in high dimensions. Okay. Maybe a more intuitive argument here is, suppose again I'm trying to learn a loss function. Here it's just a steep, high Lipschitz function, and I have a single data point. And I just want to ask the question of how well does my model match this data, right? Basic question, right, that comes to loss function generating. Well, if I look at the standard thing we would do, which is evaluate my function at the input, check the output, I get this big loss, right? And that's not right here, right? That's not really what we want, right? This very steep function matched that data point pretty well, and our loss function is not capturing that effect, right? And what's really going on here is maybe we wanted something more like graph distance, right? Maybe we want something that looks more like error in the x-axis than the vertical axis. Those two are the same up to Lipschitz constants, but the problem is we have high Lipschitz functions here, high Lipschitz data here. Okay? So these sort of insights we might take from optimization over smooth functions don't really carry over once we get into these regimes. Okay. So just a couple thoughts to keep in mind here, right? One is, for the problems that I care about, real-world data is expensive and rare, right? So we want to really be operating in this low data regime. If the function I'm trying to learn is nearly discontinuous, and this goes, here we're doing sort of prediction, but you could think of this as all for control. If it's nearly discontinuous, then there's a mismatch in terms of representation, so I need a new representation. If the thing I'm trying to learn is discontinuous, then if I use f in my loss function, then my loss function has this property as well. Arguments I would make, and we can argue about these, is one is, going back to a few slides ago, is I would be very skeptical of results from soft context simulations. If you're going to try to apply those results to a stiff system, I would take that with a grain of salt. Be very careful, because things can work really well on the soft version that don't work well on the stiff system. One thing we could do, before I sort of say what we do, is we could try to inject smoothing somehow, right, via regularization. And there's been some nice work here and elsewhere on that. But this inevitably changes the optimal solution. If I inject smoothing into my system, I'm actually changing the system. And I'm creating now a trade-off between how much smoothing I've added and the amenability to learning and optimization. Right? The more smoothing, the easier it is to learn. The less smoothing, the harder it is to learn, but maybe the more accurate my answer is. Maybe I could try some curriculum, but those things are pretty tricky to get to work in practice. So what we want to do here is reshape the loss landscape. Right? Get rid of those narrow valleys, and do so without affecting the global optimum. That's sort of the goal. So this is our basic problem again here in terms of the loss, is that this loss is not differentiable because f theta is not differentiable, the thing I'm trying to learn. So what are we going to do? We're not going to evaluate f theta. Okay, we're going to try a new loss function here. I'm never going to simulate my system. Right? I'm learning a model without simulating it. Okay. Simulating basically means find a force which matches the model. Okay, given a state and a candidate model, pick a force that matches it perfectly. That's what simulation is. Instead, we're going to optimize over forces themselves. We're going to ask for candidate forces. Okay, so this is a loss function itself now is a QP, or a QCQP, over candidate forces. Sorry, it's actually SOCP. That's a typo there. QP or an SOCP. And these two terms here are one is a physics-based, a prediction-based loss. So it says, well, a good force, okay, is one that explains the motion I've observed. Right? So I saw the cube go from here to here. Right? A force kind of corresponds to that, or a generalized force corresponds to that. A good force explains that motion. Okay? This looks a little bit like our standard prediction loss. The second law says, well, the candidate force also should match my model. Right? And we essentially, for those who've thought about the complementarity conditions, we essentially take the complementarity conditions and we turn them into a loss. Okay? With a little bit of kind of restructuring here. The reason this is convex, it turns out, because it is a QP, is the fact that we're actually not doing simulation. Right? So simulating is non-convex. We know the next state. At least we've measured it. Right? And so we're actually using that information here to make this a convex loss function. All right, so this says a good loss is one that both matches my data and matches my model. The effect here is that we actually smooth out the optimization problem. So now my sort of prediction here of force, you can do things like generate candidate forces while at a distance. It looks a little bit like smoothing the contact model, but it actually doesn't smooth the model. It just smooths out the optimization problem. Okay. So for toy problems, the landscape looks beautiful. For complicated problems, we can't draw it, but it tends to converge pretty well in practice. So what does this do in experimental data? It does really well, depending on, and it depends a little bit how much structure you give it. So if I impose a lot of structure, so if I say that I know, in fact, that I'm trying to learn a polytopic object. So an object is a polytope. Okay, so I just have to figure out where the vertices are in space. And the vertices correspond to things like sign distance and Jacobians and the like. I get this blue line down here, which basically says if I throw it 5 to 10 times, I've figured out that it's a cube. I've figured out its coefficient of friction. Okay. You basically need all the corners to hit the ground and slide a little bit, and you're good. Okay. If instead you say, no, I need more expressive power. I don't want to be so sort of tightly restricted to this idea of geometry. I want a very generalized notion of sign distance. Use a deep network. We have the line here in purple, which does well in moderate to high data regimes, as you might imagine. The more I ask it to learn, the more data it's going to require. And in the red line, we see our best attempt at using an end-to-end network here, which, as we said, does well in terms of position here in the upper left, but really struggles for things like rotation, right? Figuring out orientation. It's essentially no better than random at long-term rotation prediction, and generates large amounts of penetration along the way. Okay. Just to wrap up now, we have a long way to go here. Okay, so I think if we're thinking about becoming Iron Chefs or YouTube stars, there's a lot of work to be done. I would argue that just applying standard methods here, so whether it's standard learning methods or standard hybrid control methods to these systems, is ignoring a lot of structure, right? And not only is it, I would say, in the case of learning, is it ignoring structure that you could leverage? It's actually imposing the wrong structure, right? If I think about learning, you are imposing biases by throwing a deep network with weight regularization, for instance, at the problem. It's just a bias that doesn't match the problem you're trying to solve. So I think it's important to be thinking about ways in which to better align these processes with the tools we're going to use. We have some sort of ongoing work now doing the cube now with the robot. And maybe one thing I forgot to mention there is, so we're learning this idea of contact geometry that generates forces. We can also simultaneously learn the smooth forces. So we can say the thing I'm trying to learn is a deep network plus this contact part. And it turns out by encoding this optimization, the learning problem the way we have, the biases work for you. And it sort of naturally figures out that the smooth parts of the motion that I've observed, they go to the the non-contact deep network. And the very discontinuous things, those are generated by the contact part. Okay? there's certain things you can't disambiguate. If I take my phone and I stick it on the table and I just leave it there for a while, I can't tell whether what the mass is, for instance. It's not observable at that point. But if I take this and I start throwing it on the table and bouncing it around, I can figure out, okay, if I have some flight data, that's smooth, that's that's sort of the deep network part, and the other part that's generated by the contact model. Okay? And we're not doing this explicitly, but the biases that you impose sort of do this automatically, really. Asking for things like the simplest explanation of your data will generate this for you. I think the problem that keeps me up awake at night, and I'm happy to chat about this, is how do we get to very complex tasks, right? That kitchen task, right, at home. How do I get to something like dexterous manipulation? If I want to go and pick up objects with my hand, with my robot hand, my multi-fingered robot hand, I'm not going to do accurate prediction over random data, over tosses, right? I need some kind of structure there. I'm not going to model this as 10 contexts. I need something simpler. I need a way to get to my MPC controller, right, that can handle 3 contexts in 30 modes, not 10 contexts in 1,000 modes, right? So what is the right way to generate sort of simple models, but ones that are informative? And I think the solution we're exploring now kind of goes back to this idea of task relevance, right? Having some idea of what tasks I want to accomplish, I can use that to inform my model learning stage. But this is something that we're working on now. With that, I want to make sure I thank all the students who did the hard work here. The lab's grown a lot lately, so now we're up to 8 PhD students, postdocs, and more. And thank funders as well, so NSF, Google, and TRI in particular. And again, very happy to be here in person. Thank you for having me, Alberto, and look forward to taking questions or chatting after.
Who wants to take the first question? Hey, Pulkit.
Hello. Yeah. Thanks for your talk. So can you give some intuition about how you can do the optimization, without smoothing the model, but still get similar effect? So I saw the equations, but maybe some intuition.
Yeah. So maybe the easiest thing to see here is to say that in the example where I have no noise, the ground truth model is going to achieve 0 loss. Okay, so that's sort of one statement that doesn't take a whole lot of math to describe, but the ground truth model will pick the force the actual force in this optimization process, and it'll have 0 prediction error, and it'll match the model perfectly. Right, so we haven't changed the global optima. I think that's one key point here. As to how this generates gradients, it can do things like, say, suppose my geometry is a little bit wrong. Okay, so let's say I observed kind of an impact, right? But my prediction said there wasn't an impact yet. Right? That's my model's not quite right yet. This says, well, you observed an impact, so you probably want a little bit of force. So this law 1 is going to drive you towards predicting a force. And L2 is going to say that force doesn't match the model, but penalize it, proportionally to how well it doesn't match the model. Okay. Did that make sense at all? It's a more structured way of trying to get a loss that looks like graph distance. That's sort of our inspiration for this. It's not graph distance, because we can't compute that, but it's inspired by graph distance. Maybe one other intuitive thing you might try here, which we tried along the way and is harder to solve, is to say, suppose my state measurements are not quite right? So find, basically take this loss function up here, right? X prime minus f theta of x, and allow the x there to be wrong a little bit. So put in like x plus delta x, and then penalize delta x as well, right? That's another sort of way you might try to formulate this problem. It's not, my guess on state is not quite right, or my guess on distance to objects is not quite right, so have some penalty on that, which allows you to predict contact where you otherwise, a pure simulation would have missed it.
Thank you for your talk. In the cube's motion prediction network, given that you are already using a solver to solve the contacting force, that means you must have already know the state of the cube, and you also have a simulator. Like, how does it work if you directly use a simulator to simulate the forward motion of the cube, and how do deep neural network helps in the process?
So let me take a couple parts out. We do right now do this on motion capture. So we assume we know state. The next step is obviously to incorporate this build vision into here. And I think it's a very natural thing to do, particularly because vision is pretty good at doing things like sign distance predictions. So in terms of generating 3D occupancy. But the question about the simulator, I think it, maybe missed something, because to generate this video, right, we are simulating. Okay, I'm taking the learn model, I'm simulating. But in the training process itself, I'm never simulating. Okay, so for this video, yeah, we take the thing we've learned and we solve it. In this case, we use an LCP solver to simulate. Like, we've also used Drake to simulate as well. We could do both. But we're not doing that in the learning process. This is all trained on, given a state, predict the next state. Right? So you assume some sequence of observations. And then to simulate, you just roll that out in time for both the deep network and the content next variation. Does that answer your question?
Yeah, I'm just curious, like, if we have the state estimate, if we have already estimated the state and use a simulator to simulate the process, how accurate could that be compared to your motion capture results?
That's what we're showing here. So the rollout in green here is given the ground truth initial state, simulate forward in time, and superimpose on the true image, the true video. I feel like I might be missing the question though.
I had a question about the Carpool with soft walls. Like, what would the gap in difficulty be between like being robust to those contacts to like being able to actually exploit them?
I don't know if I can quantify that. Some of the other toy problems we've explored look more like exploitation. So we have a toy problem. This is very much a toy problem, but it looks like I have a pen and I have some fingers that can sort of go up and down the pen, and you kind of want to just walk it up without moving the fingers too much. So we can generate 80mm solutions to that problem. We can do things like, and again, toy problem, like taking a block and using fingers to rotate it, kind of like sorry, I'm going to drop my phone doing this like this, sliding and making a breaking contact. I think locally we can make these decisions, right? You perturb a little bit, you have to generate short horizon exploit contact. If I need to decide that I'm going to like reach around an object and touch it from the other side, no, you need some. That's a hybrid choice, I think, at the end of the day. You need some kind of hybrid planner to do that. But I think locally we can make pretty good decisions.
Cool.
Thanks, Michael, for the great talk. One question related to Yunzu's point. If you can go back to the block diagram when you're saying we're learning what we send to the LCP or whatever solver instead of what the LCP solver spits out. Don't you need to know much more about the geometry of the system in order to learn the inputs to the contact force solver?
We learn, if you look at like the contact force solver as like an LCP solver, what goes into the LCP, it's the continuous forces and it's the geometry, the local geometry, sign distance function and Jacobians.
So you need, for example, to know how many contact points you have between the object and
you
the
need
table.
We do have to pick a number of potential contacts. That's true. The number needs to be expressive enough, right? So for something like the cube, it needs to be at least 4, a cube against the ground, because you can have at least, particularly using vertices. It works much better if you pick at least 4, because you have four corners of contact at the ground. If you pick 4 and say they're vertices, okay, that's not going to work because you have 8 vertices. If you pick 4 and say they're deep network 4, that'll work almost as well. It works a little better if you give it 6 or 8 or something like that. The 4 kind of double up, right? Because the opposing faces can't be in contact at the same time.
So you can just pick an upper bound to.
You have to pick a number. Yeah. But you can. It seems like at least as long as you over-parameterize, you're okay.
Okay, thanks.
Yeah, good question.
Great. Are there any other questions?
If I gave you a magic wish and I could give you either a robot that was much better than anyone else's robots or a simulator that was much better than everyone else's simulators, which would you pick? Like your dream robot or your dream simulator, which would better enable your research progress?
I think we could make better videos with the robot. But maybe the simulator would be what I would actually pick, right? Because then I could simulate my imperfect robot really well and maximize its performance. That's an interesting question, though, John.
I actually want to follow up to give a third option. I heard someone saying that if your simulator doesn't sort of predict what your robot is doing, what the problem is with your controller. You should get a better controller. So I want to add a third option there: a better simulator, a better controller, or a better robot.
Well, the better controller is what we're working on for sure, more than anything else. So maybe that's what I would take, I guess. But I mean, it is an important point, Alberto, right? I mean, there's anyone who's trying to control these things, like knows that, okay, I shouldn't be generating high frequency signals on my controller because that's bad, right? Why is that bad? Well, it's not in my model, but it's still bad. And I don't know that we have a great way to formalize that intuition beyond heuristics under our policy, that style of thinking.
Any other questions? Okay, we'll take one more.
Hi, just related to Polka's question, but if you were to take the smoothing story on planning, do you think there's a fundamental gap between planning with the MIQP versus a smooth version of that and just doing a QP?
But sorry, the gap between what and what?
So if you use the smooth model for planning instead of using an MIQP, do you think there will be a gap there between the optimal plans?
Definitely, right? So this is in terms of like finding a good simple model, right? Yeah, I mean, I think that's in a way is a flaw with what we're doing now, is that we don't have any even notion that the simple model planner will produce high quality plans. We know it can, but we don't know that it will. And so I think the solution we're going to explore probably is to tightly couple those more closely, right? And I would sort of phrase it as, let's assume I know I'm planning to use a simple model planner and then some kind of QP for my control. Okay, I'm going to fix those things, and I'm going to learn the stuff that goes into them. Okay, which maybe is my simple model that I'm then going to use for planning and control. Does that give you a nice trade-off between generalization and performance, versus say something like pure end-to-end RL?
All right, I guess we're going to leave it here. Thank you.